So this is actually kind of a neat problem. We have this right here, which has essentially a pathway of reactions, right? Showing you from one to another. This is very biochemistry-like, by the way. Okay? But usually biochemistry reactions make circles. They don't end at certain things. Anyways. And then we, determine the structure of compound A, including stereochemistry if appropriate. So we look at compound A, and it's created by these conditions here, right? And so we look at these conditions, we use those to figure out what compound A would be. Now there's also a few little tricks you can play to make your life a little easier, okay? Yeah. So one of the tricks you can always play whenever you're trying to figure out the structure of something is degrees of unsaturation, right? Yeah, it's always a very nice thing, right? And you can also look at the number of carbons, number of hydrogens, number of oxygens versus this. And that pretty much tells you what has to have happened, right? Okay. So first off, we look at the degrees of unsaturation. We have 6 carbons. Should be 2 times 6 plus 2, right? It's not, though. It has a degree of unsaturation, doesn't it? Okay. Considering this is a ring, that tells me we probably have a ring, right? That would be pretty reasonable, okay? Then the next thing you can do is, well, here we have 1, 2, 3, 4, 5 carbons. Over here we have 6 of them, don't we? Okay? Here we have an oxygen, here we have an oxygen. So the number of oxygens doesn't change. We gain 1 more carbon, don't we? What else do we gain? Well, this has 2, 4, 6, 8. And then this one right here has 1, 2, 3, 4 bonds, doesn't it? So there's no hydrogens there. Okay, so that's 2, 4, 6, 8. Whoa, that's a lot more hydrogens, isn't it? In fact, that's like 4 more, isn't it? Okay. If this is starting to spark memories of other reactions we've looked at, well, it's because we've done like a bunch of these ones, right? We've done quite a few of these. And that is a Grignard reagent, right? With acid afterwards, right? Okay. And so in each of these cases, we would have added the carbon to it, right? At that positive point. And then typically this gave us O minus, and we'd add a hydrogen to it, right? Okay. Which is what we got. All right. In this case, let's think about stereochemistry. Was there any stereochemistry that was important in this one right here? Nah, there was nothing that couldn't interchange, was there? Okay, there was no cis-trans, there was no chiral carbons, there was none of that, was there? Okay, so when we add this methyl group, well, there wasn't any stereochemistry in the first place, so it could have added to either side, right? And, well, yes, I mean, if this was an unsymmetric ring, this right here would have chirality, right? It's a symmetric ring, so this doesn't have chirality, does it? Doesn't really matter which is on which side, okay? Okay, does that make sense so far? Did I confuse anybody about that last part? So it doesn't matter that you don't have to express which is forward and which is backwards, right? Because this is actually symmetric. The ring on both sides is the same, right? Okay. Does everybody understand why we got this? That was that double bond going to an O negative. Then you put the H plus on it. It becomes no negative because you have that carbanion attacking the slightly positive carbon right there, right? Okay. Are we good? Fantastic. Okay. Absolutely fantastic. All right, let's see if there's, let's do the next one.